Good evening, everyone. Welcome to the Cleveland C Sharp User Group. My name is Sam Nasser. A little bit about the group. We meet every month. The meetings are free of charge and open to the public, and it's open to a variety of different expertise levels, whether you're a student, a hobbyist, or a working professional. Everyone is welcome. We cover a variety of topics related to .NET, and you can find meeting information posted at meetup.com at the link listed at the bottom of the slide. As always, we'd like to thank our sponsors, PostSharp and DevExpress, for sponsoring the post-meeting prizes, which are given away using the eval forms. I'd also like to thank the .NET Foundation for sponsoring the Meetup website space. And last but not least, NIS Technologies for sponsoring the virtual meeting space. Some general information. First and foremost, please keep in mind participation is encouraged. And as Kevin mentioned before the start of this meeting, he is always given this meeting in a room full of people, and he always open to questions. So the only stupid question is the one not being asked. So always jump in with a question or comment, either verbally or through the chat window. However, when not speaking, kindly ask you to mute your microphones just to avoid any background noise. And we want to keep it casual but organized, meaning feel free to chime in with a question or a comment, but we want to give our speaker enough time to go through the demos and the slides. And lastly, the presentation is being recorded and will be posted on YouTube in just a few days. So for tonight's feature presentation, it is Mistakes I've Made with Relational Databases as a Developer by Kevin Griffin. Kevin joins us from the Virginia area. He's an author, teacher, mentor, and consultant. He's also a 15-time Microsoft MVP and owner of SwiftKick, which is a software training and services company. You can find his latest blog entries at consultwithgriff.com. And with that, Kevin, glad to have you with us.
Jay, thanks for having me. I'm also
Absolutely.
the president of the .NET Foundation. I forgot to add that to my bio. That'd be a nice thing to have.
Good point. Absolutely.
So if you thank the .NET Foundation, you can just thank me directly. I'm right here. I'll take all the thanks.
Much thanks for all the work you've done.
Yeah. Alrighty. Thanks, Sam. All right. Well, let's jump into it. I'm gonna rearrange my second screen real fast so I can just see everything I need to see. Like Sam said, if y'all have any questions, just feel free to interrupt me while I'm talking, or at least let me complete a thought, right? And glad to take your questions, comments. If you have any constructive feedback, that's all great. If you just want to throw tomatoes at me virtually, that can wait till the end of the session. But Sam did leave out a key word in the title of the talk, and then this session is dumb mistakes I've made with relational databases. And I kind of went back and forth on using the word dumb to describe this talk because we have a lot of lessons that we learn while we're doing our day jobs. And I don't know about you, but sometimes I'll run into a case and I'll think I know how something is supposed to work, and it turns out that's not the way it works. And I always say, Kevin, that was dumb. Why'd you do that? And I find myself having had said that so many times in my career that this talk kind of just came from that of here are just silly things I've learned the hard way, specifically relational databases. And if you weren't here for kind of the pregame show leading up to the start, I originally did this talk for a SQL Server user group many months ago, and I didn't have any database material. So this actually ended up being my database material. So that talk went extremely well. I changed it a little bit based off some of their feedback, and yeah, you all get the benefit from that today. Just word of warning, as we go through this session, I am a developer, probably like all y'all, and I'm absolutely 100% not a DBA. You would never pay me to do database administration. Everything I have learned about databases over the course of the many years of my career have come from just using databases and figuring out where things could be better, what can I do better, whatnot. If we really want to go way back, can say I am classically trained because I took a class um, for my computer science degree many years ago uh, on relational databases. And if you've ever taken a relational database class in college, you might have learned the same thing I did. They don't actually teach you SQL. They don't teach you how relational databases work. They always start with this thing called relational algebra, and it's like the math of how a relational database would work, and it's really boring. And I don't think I retained anything from that class other than the term relational algebra. Um, it would have been really useful if they taught us real stuff that we could use every day. Like, hey, here's what a select statement is. Here's what an update or delete does. Here are the 15 different types of joins you can do. That would be useful, but they didn't teach us any of that. So I had to learn a lot of this just along the way. Uh, Everything I want to talk about kind of has a slant, a bias towards SQL Server because that's what I use most professionally. But a lot of the concepts, all the concepts, also work towards other relational databases. So if you are using Postgres, if you're using MySQL or SQLite, like, these ideas still work to a degree. So don't think I'm just being a shill for SQL Server. It's just what I use every day. So I'm using a lot of the examples there. But hi, everyone. I'm Kevin. I'm just going to repeat myself a little bit. Sam already did a great job introducing me. I love Microsoft stuff. A lot of .NET, a lot of Azure. I love building business systems on the .NET platform. And if you ever want to talk to me afterwards, please feel free to reach out to me in one of the many ways here on the screen. I would love to chat with you. Now, usually when I do this talk, there's a discussion about the dumb mistakes that other people have made. And I want this discussion to be a little bit more sophisticated than what people deem the easy dumb mistakes. And what do I mean by easy dumb mistakes? So someone in the crowd would say, well, Kevin, we had this case where I had a delete clause and we forgot to put a where statement on it. Now, absolutely, that's a dumb mistake. But that's a dumb mistake that everyone makes at least 15 times, in a week. And we're not going to talk about that as a dumb mistake because that's just a thing everyone does. We're not going to talk about whether or not you should use select star versus select with defining your columns. The obvious answer is you should never use select star unless you're just playing around in the IDE. Always define your columns. Like, we're not going to talk about these easy things. We're going to be a little bit smarter ish about the type of things that we're going to discuss. So I don't have any particular order in what we're going to talk about. We're just going to jump around the different topics, and they're going to come together pretty easily towards the end. So first thing I want to do is I want to talk about normalization. And normalization or over-normalization or unnecessary normalization, this goes back to my comp sci degree. And when I took that relational database class and they taught us about relational algebra, they really started to hone in on the term normalization. If you don't know what normalization in terms of relational databases, I'll kind of break it out for you. Normalization is where we take repetitious data out of different tables and we break them out into subtables and so on. So if I had a table with say it was orders and I had addresses in the table. Well, one thing I might want to do is I want to normalize out the addresses columns into another table. And then I could reference an address from my orders table. And the biggest benefit of doing this is that you only have the data in one place and then it's referenced everywhere that it's used. So if you ever change the address, you don't have to change the address in all the different places that you use it. Instead, you just change it into one table, and then anything that's referencing it automatically benefits from that update. And this makes a ton of sense in a lot of use cases. The downside to normalization really is that sometimes we normalize unnecessarily, where I'll have a table, and I've seen this, I've done this, and I'll think, all right, I'm going to reference this in many different places. So I'll break out a sub table and I'll set up the relationships. But it turns out, in the long run, I'll end up with either a one-to-one relationship or maybe a one-to-two relationship. It's not the one-to-many or many-to-many that I think that I'm expecting. So when I'm doing queries against all this data, it's just taking a little bit more time because now I have to join these tables together. Whereas I could just have all the data in one table. All these slides should have a big old asterisk on it. And that asterisk would be, this opinion is based off certain scenarios. It doesn't apply to every scenario, but you should take it seriously when you're developing your tables and your table interactions. Maybe you don't need to normalize out that data. There's nothing wrong, at least nowadays, with repeating yourself a little bit. There was a time 20, 30, 40 years ago when relational databases were more actively used that we had an issue just with physical disk space. There was no place to put all this data. So normalization was critical because we didn't want to have all these strings of data all over the place. So normalizing it out so it's only stored once and referenced everywhere made a lot of sense in terms of disk space. Now, I don't care about disk space at all. My databases could get outrageously huge, and I really don't care because it's cents on the gig for anything that I'm trying to store. So we have actually gone back through a lot of our databases in the clients I work with daily, and we've started denormalizing a lot of our tables just to save us from some unnecessary joins. And those unnecessary joins have resulted in faster queries, and overall the database is performing a little bit better because of it. So take that for my first silly mistake I made, is that I over normalized databases that didn't necessarily need it. The second tip, and I didn't have this in the original talk, and I've talked to enough people since doing this a couple times who said I really should add in a slide about performance and basically performance opinions that you get from different blog articles and whatnot that were written pre-SSDs or pre-SSDs in the industry. Now, most of our stuff is up in the cloud. If you're running in a colo or your own data center, you're probably the odd person out because most of us are up in the cloud. But there was a time when we were all running our own machines in some way, shape, or form, and you might have had all your databases on physical spinning disks. And when we were doing that, and you had multiple spinning disks, there were a number of performance opinions of how you could go through and configure the data to be on certain disks at certain times. How would you partition a table or a set of tables across different disks? And that was all to optimize the best way to get to the data as quickly as possible. So if you knew that a certain index that you were going to hit often was on at the beginning of disk B, you know that was going to be performed because the database knew exactly where to go to get that data. Now, in terms of SSDs, and we really don't have any idea of where our disks are, what type of disks they are, how many disks there are. We really don't care about a lot of this stuff. A lot of that existing performance advice is not really useful anymore, or could actually be counterintuitive to what you're trying to achieve. And I've heard at least one or two stories of people who have followed traditional advice and is actually causing performance harm in the long run because the hardware has just changed so much over the past several years. For each rows, here is a mistake I made. This is actually the catalyst for the entire talk. Was I have a client and we deal with a massive amount of data now. And we wrote a procedure or two that basically needed to go through a whole bunch of data on a regular basis every couple minutes, and it would have to perform some analysis and transformation to that data. Now, I'm traditionally a C# developer, and SQL is kind of my second language. In the same way, JavaScript's my second language. I don't think about solving these problems in SQL. I think about solving these problems in C#, and I try to make the database just be a place where the data goes when I'm all done. So we wrote a procedure that looks very similar to this. We go get a whole bunch of data from a table, and I'm a purist. I don't use any framework. I use just good old Dapper to go get my data, and it comes back as an object. And that execute async actually should be query async now that I'm looking at it. Goes and gets all the data and brings it back. This is actually really fast. That's not a performance issue. That could have 500,000 rows. It could have 4 million rows in it. That's a fast line of code, not the performance problem. But what my dumb butt did was I decided to for each over all those different rows. And I mean, you read this and that actually works. This works all right. Let's go get all the data. Let's do all the processing in memory, and then let's do inserts into the database, or you could also do updates to the database as you're processing these different data. And this is the sort of thing that works fine in a case where you have 100 rows, maybe 500 rows, heck, even like 1,000 or 2 rows. This is not a bad solution to the problem. It just gets it done. It brute forces it. This is not, it's not ideal when you get to the 500,000, million or more. And what we found out in production was we would start doing this work and it would just take forever. Like wall time, minutes, if not hours, to go through all these different rows. And the biggest problem with this process is functionally the SQL Server is working as quickly as it can. My code's not the bottleneck. The database itself becomes the bottleneck because for every one insert or update that it's doing, it's not just doing that insert. It's got to go update all of its indexes. We have to do all this post-processing in the database to support any one individual insert. And when you're doing one or two at a time, typically not a big deal. But when you're doing much larger numbers of entities or rows, this takes significant time in the long run because this starts to get to second or two processing per row. Now expand that out to 1 million rows, and we started having some serious problems. So your solution might be, Kevin, what if you used bulk inserts, which is also a solution to that problem? And so you could take this and you could write one insert that inserts many multiple rows. And that's slightly faster, but it's slightly by like 5%. It's not a great solution to that problem. So one of the things that we did was we took a step back and realized what we're doing is just not efficient. How do you do this in the most efficient way possible? And the true solution is you have to think of the database as a processor for data sets. SQL Server, any relational database, loves working with data sets and performing operations against data sets. What it doesn't like doing is working against individual rows. So we took this process and we made a couple slight changes to it. And there's a feature, at least in .NET, called SQL bulk copy. So what we do is we go off and we do all of our processing, and we do this all in memory, basically. Or we could do chunks of it in memory. And so we build these large data sets, and we use one of my least favorite data structures, the data table. If you're going to use a data table, only use it for this. This is, in my opinion, the only useful reason to use a data table, because it's a huge memory hog. But it's really good for this particular purpose, because you can take that data table, you can tell SQL bulk copy, which is built into .NET. I want to take everything inside of this data table, and I want to create a new destination table in my database called staging 123. You can call it whatever you want, and it takes all the data in your data table and just dumps it into the database, and it does all this stuff underneath the scenes where it bypasses transaction logs, and it just gets the data into the database the way that you want it to. So we did this, and then we had a simple update script that we ran on the database that would compare the new data coming in, and it would perform the subsequent inserts or updates to the tables that we're actually trying to update. And the the wall time saved. So this process, let's say this took 10 minutes to run, 10, 15 minutes for several million rows. This process took about 10, 15 seconds to do the exact same thing with the exact same data. It's a night and day difference. And that's simply because we're thinking about the data in terms of data sets instead of just raw for each through every individual row. And that's because I'm a C# developer. I think about going through this data iteratively. But in the database, we don't want to do that. We want to think in terms of data sets. I figured a lot of this out because I really sat down to try to learn and understand what an execution plan. And that leads me to my next big revelation. Was I had a conversation with a very good friend of mine who's also primarily a developer, but really went deep into databases in his career. And he said, well, what's the execution plan say for various queries I was doing? I'm like, I don't know. What is an execution plan, and how do I read one of these? So if you're asking yourself that question as well, an execution plan is simply the blueprint for how the database will execute a given query. So here's an example. If I say select select stuff from a table, and maybe I throw in some joins, or I do some aggregations, or I need to do some counting. The database is going to take that query and it's going to break it up into all of its relative steps. So here on the screen, you can see I'm talking to an index, and it's going to do some aggregation. That's my count. So it's going to count how much stuff comes back from the index. Has to do some computations, but because it's two separate queries, it's got to do this join, but it's got to do it iteratively. So it's got to put everything together. And then finally, it does more computation to figure out what exactly I was originally asking for. And at the end, I get my select. Now, it's probably difficult to see in this screenshot because we're screen sharing the various arrows that move between the different stages of the execution plan have different thicknesses. And when you're in SQL Server and you're looking at execution plan, the thicker the arrow is, the more expensive the query is in the long run. You have a lot of data, a lot of work that's being done. If I was doing a talk simply on execution plans, we could spend another couple hours just going into each section of this execution plan and saying, why is this efficient versus not efficient? And spending time on discussing how do you optimize this, how you optimize that. And if it's an expensive query that you're running often, you probably want to spend the time learning to optimize that stuff. If it's an expensive query you want to run once or twice, maybe it's something you don't touch right away. Again, this is a thing where it really depends. But once you get into execution plans, you're going to start learning that there's just a couple key things you can start looking for, and minor optimizations you can make that will make most of your queries much more performant. That leads us on to the understanding of scans and seeks. So when you get into execution plans and you learn how the database actually pulls data out of the various tables or the various views that you have created, it really comes down to, are we scanning the data in the database table, or are we seeking the data in the database table or in our indexes? So what's what? When we have a database seek, it means we can quickly just reference the data that, I'm sorry, when we do a database seek, we have to go through the data, and once we find the data we're looking for, we just stop. We know exactly where it is. When we do a scan means we have to go through all the data until we find what we're looking for, and we might have to scan multiple times to ensure that we're finding everything that we need. Now it probably doesn't make a lick of sense. So let me show you an illustration, and hopefully this makes it a little bit clearer. Let's say I have a database table, and that database table has a bunch of dates in it, and they're just integer for years. And I want to go get all the employees who were hired in the year 2000. Well, if I don't have an index on my date column, this becomes a database scan. The database has to go through and has to scan every row looking for the ones that match the criteria. So this query will scan the first item, second item, third item, fourth item. Hey, I found someone who matches that criteria. You would think, well, all right, database is done. It found what it was looking for. But it might not be the only one. So it has to keep scanning even more, even more, even more, even more, until it's gone through the entire table. And there are some cases where it might have to go through the table multiple times to find every row that matches the criteria that you're asking. Now, again, if this is 10 rows in a table, it's not a big deal. Scan to your heart's delight. But if you have a couple million rows, you might really want to set up an index on the column that you're referencing. So in this case, hire year. And this would turn the hire year from a scan into a database seek. So the seek means I know exactly what I'm looking for because the data is ordered. So I can say, I want to find all the employees where the hire year is the year 2000. And database just knows, boom, here it is, I have it. And it doesn't have to keep looking down the index because it already has all the data that it's expecting. So this, right off the bat, will make a lot of your queries just much more efficient because it will, you're just going right to the data that you want. It doesn't have to go through every single row every single time. Now, once I learned this idea of the scans versus seek, I learned I really need to start building better indexes, because a lot of the indexes you just get out of the box are usually around your primary key or maybe your foreign key relationships, depending on how you're setting your tables up. And for things like this query, I'm not going to get that index for free unless hire year was some part of a key. So I need to take the responsibility of going in and creating these indexes for myself. And a big part of that is just looking at the queries that you're running. So one of the cool things that SQL Server will do for you is if you're looking at your execution plans, it will often tell you or suggest a certain index that you might be missing. So here's a random complicated query that I created. And if I run it, it'll say, hey, you would benefit from having an index on one of the columns. So probably state province ID in this example. And you can see in the execution plan on the very right side, we're doing index scan, which means we have to look through the entire index or the entire table to find what we're looking for. And this is costly because if we're doing joins, means we might have to hit this table multiple times. And just overall, this is an expensive query. And it's to the point where SQL Server saying your life would be so much easier if you just had this index. And it's probably right. If you were to right click on that, it would give you the SQL to create the index. And that happens almost immediately. And if you rerun this query, the query would be faster. And remember, again, it's all relative. There's a couple hundred rows in the table, probably not a big difference. There's not going to be a wall time difference. But if you had millions of rows, this makes a big difference in the grand scheme of things. So when it comes to indexing, there's a lot of really good articles out there on it. There's a lot of good talks. I have just a couple general rules that I follow when creating indexes, and I try to create some of my indexes when I'm working with mission critical or sorry, maybe not mission critical. It's a bad term. Just queries that are going to be run often. I try to write a lot of my own indexes because I know how those tables are going to interact with each other. So a couple rules I follow. First is always index on foreign keys. So this helps with joining. If you have a query and you're going to join table A to table B, make sure you have indexes on the keys or the items that are being joined upon. Because then you're just telling the database, when you're bringing in table B, just go to this section of the index. Those are the items that you want to join on. And it helps the database do its job. If you're using a column anywhere in a where clause, join, or an order by, you really should probably have an index on those columns as well, because now you're telling the database, here's where you can go short circuit a lot of the scans that you would normally have to do. I'm just going to give you the data that's pre-computed. When you're doing this, though, you also need to remember that the order of the columns in an index can matter. So if you're indexing on 3, 4, 5 columns, which might be a lot, you want to make sure you index on the one that's least likely to change and kind of work your way up there. That I can't give you a good example of that, but just know that the column order really does matter. But at the same time, don't create the index for every single column in the database. A great lesson I learned was to create what are called covering indexes. So in the previous slide, I had employees where the hire date was the year 2000. If I was creating an index for that, I would index on hire date, but I would then create the covering index to return first name, last name. I forgot what else was, so maybe address. So just the columns that I need for that particular query. If I'm running that query often enough, I've now made it dumb simple for the database to go look at my index, grab the handful of rows that I care about, given the where clause, and it returns exactly the columns that I need. If you don't do that, you now have to give the database an extra step where it goes and pulls your index and knows, all right, 10 columns match the index. We know what the 10 rows are. Let's go get the other data. And there's a term for it. I don't remember what it is, but it's like, oh, yeah, see how prepared I am. There's a term for it where it has to go look up all the data after the fact. And it brings that back so you can actually get all the data that you care about. So set up covering index, and hopefully that helps with the majority of your queries. To the same degree, if you're using something like Azure SQL, which I use a lot, one of the cool features that they have is automatic index creation and regression testing. If you don't have it turned on, and you're using SQL Azure, I highly recommend it because it's been insanely useful to us, where we'll create queries, we'll create tables, and we don't necessarily go through and do a first run on indexes. We'll let it just run for a little bit in our test environment, and we find it will automatically create the most critical indexes for us automatically. And what's even better about that is it creates the indexes and it watches the performance of all the queries to see if any queries regress in performance because of a bad index. And if it sees that, it's going to automatically drop the index on your behalf if you allow it. Now, I say that because the next piece of advice with indexes is that if you change your queries at all, you should really go double check all your indexes. If we talk about the covering indexes, you might create this great index, and it speeds up your a couple of your queries, makes them nanosecond performance. They're so blazing fast. But then you go and change the query. And when the query changes, the query analyzer has to figure out the best way, the best execution plan to solving that problem. And it might not include the index that you originally thought it was using. It might just go off and have to change your scan into a seek, or I'm sorry, your seek into a scan. And now you've gone from nanosecond queries to wall second minutes for a query. And it's not ideally what you want. You don't want to go backwards in performance. So if you're making a huge change to a query, always make sure you check your indexes as well, just because you might have accidentally slowed things down and you didn't want to. So, and that's the last tip. Always check the execution plan. And these are for mission critical queries. We have hundreds, if not thousands, of queries in our applications, but there are usually just a dozen or two that we deem, the mission critical ones that are doing the big heavy lifting. We usually always have some sort of test version of those scripts, so we can go see what is it doing underneath the scenes. And if we make big changes to those tables, we go check the queries and we check the execution plans just to make sure that we didn't break anything. Next big piece of advice. I grew up on a team that hated nulls in the database. And this was an extension of just being C# developers. Was we don't like nulls. Like a null reference exception could be the bane of all of our existences. Nulls are bad. Nulls that you're not expecting are bad. So we had a rule that we weren't allowed to use nulls in our database tables. And what ended up happening was we had conditions where, so here's an example, and we are using a null here, where like description. So description was not nullable. And what happens if you have a case where there's no description? Well, we would put in empty strings. And now there was this requirement on us to make sure that we had maybe default values on these tables, or our code was making sure that the properties were populated with something. It meant we were doing a lot of dancing around the data aspect of it. And then we were running these cases where we had a table, maybe we need to add a column or two to it. And we kept to our rule that it had to be not null. Well, now we had to go figure out what was the default value of these properties when we added them. Did we need to write a script to go back and calculate and fill in blanks where we would normally just have nulls? It made just doing regular database work really complicated and cumbersome. So as I just kind of progressed through my career, I started using nulls more and more often where it made sense. So things like strings or varchars, if I knew there was a possibility that there was not going to be a value for that, and it was okay to not have a value for that, we would just start using nulls. And now you have to do your null checks on the server side. So after you pull the data from the database, do your null checks. Don't make things complicated on yourself and like make a date time nullable. That just makes your C# so much more difficult to read because now you have to use nullable types and whatnot. But there are probably cases where you would think, the absence of a value in this column is perfectly okay. And yeah, just use the null. Don't force yourself to have a default value for every single column in your database. I have a couple good stories. So we had a feature in one of our products. So one of the main clients I work with right now, we have multiple products, and one of our products, we were using a feature in SQL Server called system version tables. And what a system version table does is whenever you make a change to a row, any row, any column, it does a snapshot of the changes and puts it into another table altogether, and it's called the history table. And what you can do is anytime you can say, show me the changes made to this row uh, within any period of time. And it'll show you, all right, here was this version of the row, and here was the next version of the row, and so on and so on. And we had a perfectly legitimate reason for using that feature because we have a lot of people working in the data, and we don't necessarily trust the people that was working in the data. So we want to have an audit log of what was changed by whom, and system version tables was the mechanism for solving that problem. Cool, worked great. A colleague of mine, he's not a colleague anymore. He left for a completely different reason, not for this. He saw that we're using system version tables, and he had a similar problem. At least he thought he had a similar problem. And he was looking at what we were doing with system version tables, and he goes, I like that. I think I'm going to implement that on one of the tables that we're working on. So, okay. So he went off and he did that. He implemented system version tables so he could track the changes to a row over time. And what had happened was he added this to a table that he also had created triggers on. So there was a trigger on the table where every time it was updated, it would go back and update a different column. And I think it was just like the date updated column. And it would do all this with a trigger. Now, typically I don't like triggers, but this was a legit use case. I didn't see a problem with it. Except he never considered how do these two useful features by themselves work with or against each other. And what ended up happening in this case was we had deployed his feature that used system version tables, and we did a snapshot of the database. And this database normally sits around 3-4 gigs in size. Okay, that's just normal usage. And we did a snapshot, and it was 40 gigs. And so I know I can't see your all faces, but I'm hoping you're gasping. You're like, oh man, that's quite a bit bigger than 3-4 gigs typical. Like 40 gigs. How did it get this big? And it was because our history table was ginormous. Even with retention turned on, it was just growing exponentially out of control. And what was ending up happening is every time we would update one of these rows, it would then create another row in the table for the date updated. So any one updated would produce 2 columns or 2 additional rows in the history table. And for a database that gets frequent use, it was just growing this table exponentially. So we went back and went, okay, do you really need system version tables? And the answer was no. So we took that out. I think we left the triggers in there, but I'm not entirely sure. But when you're using different features, spend a moment to think, are we doing anything else here that might impact this feature and how we're using it? So that also leads us to kind of the last thought, and I touched on this a little bit, is you really don't need to use all the features of your database. Just because it's there doesn't mean you have to put it into production. System version tables was a great example. He was pushing system version tables because he wanted to track the changes of the table. Now, that sounds good, but we went a little bit deeper. Why do you want to track the changes of the table? He said, well, I really don't want to track the changes of the entire table. I really just care about the changes to one particular column. Okay, well, do you need to save the entire row to track the changes to one column? And the answer is no. The simpler solution of that problem was we just had 2 columns. So anytime a column changed, we would just save the previous version of it or previous instance of it. Taking that out, drop the database size from 40 gigs all the way back down to the proper 3-4 gigs that we were expecting it to be. So yeah, just a net positive across the board. So if you're thinking about using a fancy feature in whatever database that you're using, think about, is this something I actually need, or am I just trying to use the shiny feature for the sake of using the shiny feature? But so I've been talking for a long time, and no one's really chimed in with any questions or comments or anything. So I kind of just leave it to the last slide. Is what are your fun stories from the trenches? Anything I missed? Anything you want to correct me on? I love this part of the discussion. I've never done it virtually before, so if anyone wants to chime in, now is the time. This is a safe space. Like no one's going to judge you ill for anything you've done, or just blame it on your coworker, Bob.
We have a comment in the chat window from Stephen Ball where he says, I've run into this in the vendor's database where instead of nulls, they use tab characters. And
Mm.
my
Oh my
thoughts
gosh!
exactly. And so I chimed in as well, and I said tabs or empty spaces are typically a nightmare because you can't see them.
Yep.
And unless you're looking for them or you know how to trim them, it can be a nightmare. And not just in working in SQL, but also working in .NET as well. I remember we had a problem with one of my clients where we were doing some things with AD, and one of the usernames, for whatever reason, he entered a space first, and when searching on it, it wouldn't come up
Yep.
time after time, and it frustrated a lot of people until eventually we figured it out.
And then you think, all right, the solution to this is when we're doing the query, let's just trim all the strings. Let's trim all of our varchar characters. But now you're adding an additional step to any query that you're running, because not only do you have to go get the however many 100,000 million rows from your table, now you have to go through every value in that column, trim it, which is a string operation, which isn't faster just because it's SQL Server. It's still a string operation. So it has to trim all these strings, and then it can actually go do the filtering that it was meant to do. So you just instantly slow this thing down. I have run into that more times than not. I've also
Right.
run into where um, we had data in there, so we were doing a filter with it had a single quote in it, but the data coming in wasn't the just traditional single quote. It was like the fancy Unicode single quote, like the stylized one. I forgot what the code is, but unless you tell SQL Server specifically to like change its collation to search for that stuff, it never finds it. So we had queries that were just failing because of Unicode BS. It's all awful. It's all awful.
Right. And the other thing I found is when you have those tabs, if you like, I'll try to do that. I'll try to do a replace to make sure I remove any tab characters before I export the results.
Yeah.
But if I miss one and then you go drop those into Excel, all of your columns are now a mess and your report is
Yep.
junk.
Oh, yes, it is. Man, I would give you empty string. Like we've done that more times than I can count. But tab characters, like that is a just different level of evil.
I was also shaking my head when you were talking about nulls. And so I think nulls could also serve a purpose where they provide an extra value in the sense that, let's say you're utilizing a Boolean type column. Obviously,
Mm-hmm.
those values are either true or false, right? But let's say you're using that column to indicate if a person had voted
Yeah.
or what that person vote was. So it'd be, obviously true or false. But then if they never voted, you could use the null, make it a nullable Boolean to indicate that they didn't vote at all.
Yeah.
And so it helps to fill that extra value, if you will.
Yeah. Yeah. We really have to think of nulls as the absence of the value. And is this a column that could just not have a value at all? And it's okay to have that null. As long as you're safely programming around it, like you have to still practice all null safety.
Exactly. Anyone else have any comments or war stories, as we mentioned,
Yeah.
they'd like to share?
I have a question. How often do you recommend, like you work with big data, it sounds like, huge size databases, how often do you back up? And what is your recovery procedure for something of that size?
Yeah, so the majority, all our production databases are in SQL Azure, and those have point in time restore. So I can restore to any point in time that I need to. Um, the Now we practiced this a couple times. So the restore process for a couple gig database can take about 10 minutes, 10, 15 minutes. The It's not directly overriding the database that was backed up from. You always have to restore it to a separate database, and then we have scripts that will compare or replace the data that we're trying to restore from. Uh, it's one of those things where we've had to do it manually a couple times until we learned what processes we needed to build. Thankfully, we don't. Knock on wood. We haven't had to do it in a while, but there's one of the reasons we use SQL Azure is simply because it has point in time restore. We know that the database was good at a certain point in time. We can go back to that point in time, and the data is 100% intact where it was. And then we have change scripts that will fix the data if we needed to.
Okay, thank you.
But so I guess want to answer your question. If I was hosting the database myself, so maybe I had on my own hardware or I had a VM or something like that. I mean, it really depends on the business and how mission critical the data is. The data we have doesn't necessarily need point in time restore. We would be good with a full backup every week and then incremental backups throughout the week, maybe every 6 hours or so. The Most of the data we would lose in that time, if we did, we could rebuild pretty quickly. It really depends on the organization, how mission critical the data is. You might have a little bit stricter backup regimen, but also remember backups take up space. So, but we really don't care about that stuff from where we are because just seems like you can have terabytes and terabytes of data and it doesn't really cost you anything.
Okay,
That's
thank
also
you.
where my DBA, like I should have a DBA hat and I don't. Like a DBA is much more qualified to answer that question than I am.
I just wanted to chime in also in addition to that, of course, it depends on how valuable your data is, how much you're willing to lose, but also if there is, let's say, one or two tables that have critical data that you need up to the minute, you can also utilize the temporal tables like Kevin talked about earlier, where it stores any updates, and so you literally have up to a point in time restore if needed, and it's on the fly. You don't need to restore
Yeah.
from a backup. It's immediately in the database. But also, what I liked about when you mentioned that, you said just because it's there doesn't mean you should use it, which, in my opinion, is the second universal rule right behind if it's not broke, don't fix it.
Yep. Yeah, the temporal tables sound really good on paper, but once you put them into action, you think for any one row that you have in the database, you could potentially have two or more versions of that row in your temporal table. And for us, we actually had to change a lot of our processes because we found that we had a lot of data coming in. So just explain what we do is we have a lot of ingress data coming in, and we're talking hundreds of megabytes worth of just CSV data. And what we do is we go through a whole bunch of post processing on this data, and it eventually ends up into our regular tables. And we've been doing this for 20 years. So we have a lot of data, and a lot of that data doesn't change. It's the data we had before. After we do all of our post processing, it's exactly what we already have in the database. And we learned that we were updating the database, and all we were doing was changing the date updated flag in the table. And every time we did that, it would update our temporal table as well. So I would have 50 instances of this row, of a row, and the only difference between all of them was the date that it was updated. We didn't actually change any data. So we went back and we rewrote our process to make sure, is there actually a delta to the row I have now to the row I'm going to be updating, because we were just polluting our temporal table. And we had the same problem I kind of talked about before, where the database was a reasonable couple gigs, and then it just ballooned into this bigger size. And then, so we did all this work to cut down on we're actually putting changed data into the temporal table. And then we added a retention policy. So how long do you want to retain the history? By default, it just retains it all, unless you tell it only retain for a couple of days or retain for a month or two, whatever policy you want. For us, we just said retain it for a month, I think was all we cared about. And that significantly shrunk down the size of our table, or it's more consistent now. So our data can grow, but the temporal table stays pretty consistent. It's just things you learn the hard way. Like, it's probably in the documentation. Like, if I went to Microsoft Learn and just read documents after document after document, I'm sure there's a little paragraph there that says, hey, here's something you really should know. And I could just stare at the documentation and I would still just gloss over it. It's not until you start running into these situations, you start going, hey, I bet someone wrote documentation on this. 9 times out of 10, they did.
But as always, the best lessons learned are the ones that cause the most pain.
Absolutely.
Unfortunately, no two ways about it.
That's why your dollar value goes up as you progress in your career. It's because you've just learned more.
Because you've endured more pain.
Yep.
Yeah, exactly. All right. Any other questions or comments for Kevin?
I really appreciate you all hanging out with me today.
Thank you, Kevin. Very insightful. Always good to hear stories from the trenches. So definitely appreciate you putting this together and joining us tonight.
Hey, my pleasure. Thank you for inviting me.
Thank you. And I have just a couple concluding slides before we adjourn for the evening. All right. So as mentioned earlier, the meeting is being recorded and will be posted on YouTube. And you'll notice that there's a variety of links in the chat window. If you would please utilize that link and subscribe to it to get upload notifications. And likewise for my blog as well, where I post tech events, you can subscribe to that to get the upload notifications. And more importantly, the feedback eval. Please take a moment to fill that out and provide Kevin with some constructive criticism. It would be highly appreciated. For those that are in the job market, please check out devitjobs.com. It's a pretty interesting website where it breaks down, or you can filter by technology, location, working remotely or in person. So if you're in the job market or looking to transition, feel free to check that out. Lastly, my contact information. My email is snasser@nistechnologies.com. You can also find all my socials on Linktree. And if we're not connected on LinkedIn, I invite you to do so. And so with that, thanks again to Kevin, and thanks for all who attended, and look forward to seeing you all next month. Good night, everyone.